So this is a discussion of Archimedes' principle. Um, Archimedes lived around 250 BC. His king was Hiero II, and Hiero tasked Archimedes with the job of determining whether his crown, Hiero's crown, was made of gold, as the jeweler had said it was. And so this is a typical crown. If you think of those ancient Greek crowns, imagine a picture of Julius Caesar. They had these viney things on their heads with little leaves of gold sticking out, and so they look something like this. Archimedes couldn't easily melt this down because it had been made, sculpted, you might say, and so he had to find some way of determining the density of this object, or just whether or not it was gold without destroying it. And so he had his eureka moment when he got into the bathtub, right? And so we're gonna sort of depict this as a section of water here, and I'm gonna have an object down in the water, and I'm gonna pick a cylinder because the geometry is gonna make the math easier for us. And then this isn't exactly what Archimedes did, but it's okay, right? And so here's my cylinder, right? Let me just try one more time on that bottom piece, make it look a little better. It's always hard when you're doing the last one. And so this could be a piece of wood or a piece of metal, a battery. It could be just an imaginary section of the water. All we know is that this piece of material is cylinder shape and is sitting down under the water. The top of the cylinder is at a height h1, and the bottom of the cylinder is at a height h2, right? The area of this cylinder is, top and bottom is A, and so the height of the cylinder is h, which is just h2 minus h1, right? And so, so if you talk about the forces acting on this, I'll go back to yellow. There's an F1, which is just a fluid above the cylinder pushing down on the top, and there's an F2, which is the fluid at the bottom of the cylinder pushing up on the bottom, right? There are also forces on the sides of the cylinder due to the fluid, but they're not contributing to whether the cylinder sinks or floats. They're just horizontal forces that cancel each other out all the way around. And so we're going to be interested in these F1 and F2. Now the buoyant force is just F2 minus F1, right? F2 points up, F1 points down. If F2 is greater than F1, the object will go up. If F1 is greater than F2, the object will go down. And so this determines what the object does. If we want to talk about what F1 is, we can say, well, F1 is just the pressure at 1 times the area, right? Because force is pressure times the area. And so whatever the pressure is, P1 is just the pressure at that point, right? Similarly, we call this P2. Right, and so F2 is equal to P2 times A2. And now remember the pressure at a depth in the fluid is P is equal to rho times G times H. We saw that earlier. And so I can say, look, P1 is equal to rho G H1, and P2 is equal to rho G H2. Right? And so now I can say the buoyant force is just P1 times the area, P2 times the area minus P1 times the area, right? And so that's rho G times H2 times the area minus rho G H1 times the area, but I can write that as rho G times the area times H2 minus H1. Right, that gives me the, I've just done included a little algebra there. And so that means that the buoyant force is just rho G times the area times the height of the cylinder, right? But what is that? The area times the height of the cylinder is just the volume of the cylinder, right? And so that's just rho times G times the volume of the cylinder, right? But rho times the volume is just rho times the volume is just the mass of the displaced water. Right? The volume of the cylinder times rho is just the mass of an equivalent amount of water that would fill this cylinder. And so this is just the mass of the displaced water times g. And so the buoyant force is just equal to the weight of the displaced water. Let me try that again. And so when you submerge something in a fluid, Archimedes' principle says the buoyant force, the upward force, is the weight of the fluid that's been displaced.